Welcome back to School of Physics. Today in this lecture I'm going to discuss a few things like velocity and acceleration, as you can see in the polar coordinates. Okay, so earlier we were discussing the velocity and acceleration in Cartesian coordinates only, but we know in physics it is very much essential to know about the polar coordinate systems also. So for that we will be dealing with the velocity and acceleration in polar coordinates also. So for that, furthermore, we can discuss about force and its components in these coordinate systems as well. So to understand force and other kind of forces which are occurring in the nature, to understand them better, for that first and foremost we have to discuss and understand this very concept about velocity and acceleration also. So further, as the time proceeds, we will get an adequate knowledge about the concepts further. So first and foremost, starting with, we will be dealing first, I will be discussing the orthogonal Cartesian coordinate system. Cartesian coordinate system. Okay, so if we'll discuss this, we have to consider, for example, I am giving you a simple example. I will consider a particle along a circular path, along a circular path. For example, what I'm saying is that, say, this is the circular path which is along which the particle is moving. Say, for example, this is the particle, and suppose that we at the center we are the Cartesian coordinate system is drawn like this, with its origin at the center of the circular path. Okay, so this is the Cartesian coordinate system and this is the origin of it. Fine. So this very particle, this is x-axis and this is y-axis. This is a plane Cartesian coordinate system. Okay, so this very particle is moving along the circular path, making some angle from the initial stage. For example, it starts from this very point, and after some time it will cover a distance which is here. It will be calculated in terms of theta. Okay, so this will be the theta which it traverses along the time as the time passes. And furthermore, you have to keep it in mind that along this very axis you are taking the position vector r. Okay, this is the position vector, this along the particle from the center toward the particle, it gives the position vector. And along this very axis, this will give the change in this theta. Fine, change in the angle traversed by the particle with respect to time, within the time. Okay, this is the position unit vector and this is the angular unit vector, that is theta hat. Fine, so this is the xy axis, this is the orthogonal coordinate system. So we know, it is the basics actually, the position vector r for this point, for this particle which is moving along this circular path. Position vector r will be given as, say for example, from the center up to this circle, that is the radius of the circular path, or simply the circle, say it is a. Fine, so we have r will be equal to, r is the position vector, keep that in mind, r is the position vector, position vector, that is, it gives the position of the particle at any instant of time. Fine. So our vector is equal to a, this is the magnitude of the vector a multiplied by cosine of theta I. I is the vector, unit vector along the x-axis, plus sine of theta along the y-axis, unit vector along the y-axis. Okay. So from where it is got, it is very much simple. You can check it out here. For example, for any position vector, for any vector in the Cartesian coordinate system, how do we write it? Say we are writing R. It's a position vector here. So for example, it's any vector in the Cartesian coordinate system. It is represented by x component along, this is the x magnitude of the vector along x-axis plus along the y-axis. Say y magnitude along the y-axis is represented. This is the general representation of any vector in the Cartesian coordinate system. However, we can write it in the, since here it is moving along the circular path. It's moving along the circular path, so we can write it down as R is equal to a times x divided by a. I'm dividing throughout by a, okay? I plus y by a j hat. Fine. So x by a is here. This is the position vector. It is here a. Here the particle is here. This is the origin O, and this is the along the x-axis. This is the x-axis here. So draw a perpendicular on the x-axis. Fine. From the Pythagorean theorem, what we can deduce, this is the theta. Fine. So cosine of theta will be equal to, this is the x and this is the y, for example, say. So cosine of theta will be equal to base by hypotenuse, that is x by a. Fine. And sine of theta will be equals perpendicular, that is y here, divided by hypotenuse, that's y by a. So y by a is sine and x by a is cosine. So r will be equal to a times cosine of I theta, cosine of theta I plus sine of theta along y-axis. That is what I have wrote here. Okay, this is simple, so understand to get this very thing. So here is the position vector in the Cartesian coordinate system. So R is equal to a times cosine of this and sine of this. Fine. Now we have to get the, I told you we have to calculate the acceleration and velocity. So to calculate acceleration, we have to know what its velocity is. And the velocity, what does velocity mean? Velocity means we write velocity as dx simple in the, if it's moving along the x-axis only, dx by dt. That is the differentiation of position vector with respect to time. Okay, so we have to differentiate the position vector with respect to time to get the what? Velocity. So differentiating with respect to time, that means dr by dt. That's also represented as, it's written down as r dot. Okay, this is the Newtonian representation, keep it in mind. R dot means dr by dt. So dot means differentiation with respect to time. So differentiating this with respect to time, since a is the constant here, a is this, the vector, this radius of the circle path. Okay, so r dot will be equal to, this will be written as it is. Differentiation will be done on cosine of theta and sine of theta. Keep this in mind that theta is varying with respect to time. Okay, we are changing the theta. Fine. So we have to differentiate cos then theta also from the chain rule of differentiation. So you might have already done that. So cosine of theta differentiation is minus sine of theta into multiplied by differentiation of theta, that is with respect to time, that will be theta dot, okay, plus differentiation of sine is cosine of theta, and the differentiation of theta itself, what will be that? D by dt of theta, that is written as theta dot, along, this is along x-axis, that's I, this along j-axis, that is j. Fine, keep this out. A times sine of theta along I plus cosine of theta along j. Theta dot, keep this at outside, so we will get theta dot here. Fine. So this will give the velocity of this very particle along the circular path, and this here we can, you have to remember this very thing, this gives the direction here, this gives the direction of increase or decrease, whatever the case may be, increase in theta, that's the angle. Okay, fine, this gives the direction of the change in the theta. So it may be represented, we can surely represent this very thing, it is denoted or represented as the unit vector like theta dot, theta hat. Fine, so this gives the change in the angle theta, this very component, sorry, it's minus times sine of this and plus times cosine of this. This gives the change in the angle theta. Fine, this is represented by theta hat. So we can represent this very thing as R dot will be equal to A times theta dot, and this is theta hat. This will give the velocity in Cartesian coordinate system orthogonal. This is an orthogonal coordinate system, keep it in mind. Fine, so we will get the velocity equal to this. Now we have to calculate the acceleration, and acceleration means the double differentiation of position vector. So first differentiation we got this, now we have to differentiation it again. We will differentiation this very equation again with respect to time. Say this is equation A.